Welcome back. Let's practice finding level curves and sketching contour maps. Alright, so here's our first example. We want to describe the level curves of the function and sketch a contour map of the surface. And our function is f of xy is equal to x plus y. Alright, so the first thing we want to do here is find an equation that will help us find level curves, and then sketch some level curves in this xy plane to create a contour map, which will help us visualize the surface represented by the function that we've been given. And so the way we do that is by setting the multivariable function equal to a constant value. I like to represent that constant value with c. We're going to set c equal to the function x plus y. Now, at this point, you want to try to get the equation in a form of some type of curve that you know how to graph in the xy plane. And in this case, notice that if we were to subtract x from both sides of the equation, we will just have the equation of a line. All right, switching the sides of the equation, we would get y is equal to negative x plus c, right? Subtracting x from both sides of the equation just leaves you with y equals negative x plus c, which is just the equation of a line. It's a line with a slope of -1 and a y-intercept of c. That is how we would describe the level curves of this function. Okay, so now that we know in general what our level curves will look like, let's actually find a couple level curves and then graph them in this plane to sketch a contour map. And I always like to start with c equals 0. I like to let my constant be equal to 0 and see what happens. If c is equal to 0, you'll get an equation of y equals negative x, right? You'll have negative x plus 0, which is just negative x. So that's the equation we get for c equals 0. And now let's choose another value for c. And when you pick your values of c, try to pick them such that they are evenly spaced apart. So what I'm going to do is either increase or decrease my value of c by 1 every time. That's typically the way I recommend you go about these problems. By picking evenly spaced values of c, you'll get a nice contour map that gives you a decent visual of the shape of the surface represented by your multivariable function. Okay, you don't have to pick them evenly spaced apart, but it's usually best practice to do so. Alright, so I'm going to pick c equals 1 as my next value of c, and when c equals 1, the equation will be y equals negative x plus 1. Alright, so y equals negative x plus 1. And then let's look at another value of c. I'll increase by 1 again, so we'll have c equals 2. And so that's just going to change the y-intercept. The equation will be y equals negative x plus 2. And then let's look at another one. Let's look at c equals 3. When c equals 3, that will be the y-intercept for the line. So we get y equals negative x plus 3. And that's probably enough. We could go to c equals 4, c equals 5, and so on. But before we start graphing any of these level curves in our xy plane, I will look at least one negative value of c. If it makes sense to use a negative value of c for your function, feel free to do that. It won't always make sense to do so because some functions don't output negative values, right? You're saying that c is equal essentially to the output of the function. So if it can't ever be negative, you wouldn't want to pick a negative value for c. But in this case, x plus y could be negative. It's not always going to be positive. So let's just look at one negative value of c. C equals -1. It just decreased by 1 from our initial value of c equals 0. So the spacing is still equal here. All of our values of c increase or decrease by increments of 1. And when c equals -1, you'll have negative x minus 1. All right, y will be equal to negative x minus 1. All right, so now let's graph these level curves, or really they're lines, but let's graph them in this xy plane. I'm going to say that this is y equals 1, 2, 3, and 4. And this is x equals 1, 2, 3, and 4. All right, so that means that this is y equals -1, -2, -3, and -4. And then x equals -1, -2, -3, and -4. All right, and then starting with c equals 0, the line is y equals negative x. That's just a line that cuts through the origin with a slope of -1. So that will look something like this. That would be our line, or a level curve, for c equals 0. Then let's do c equals 1. It's the same line, but with a y-intercept of 1. So we're going to draw the same line, except shifted up 1 unit in the y direction. So that line will look something like this. That will be the line, or level curve, for c equals 1. And the same thing is going to happen for the rest of our curves. For c equals 2, we're going to shift up another unit in the y direction because the y-intercept is 2. And then for c equals 3, we'll shift up another unit in the y direction because the y-intercept is 3. Okay? And for c equals -1, we're going in the opposite direction. We're shifting down 1 unit from just y equals -x. The y-intercept is -1, so that line will be down here. All right, so let's draw all these lines. Starting with c equals 2, we have a y-intercept of 2, so that will look something like that. That is the line, or the level curve, for c equals 2. Then for c equals 3, we'll have a y-intercept of y equals 3, and so that line would be the level curve for c equals 3. And then for c equals -1, we want to cut through the y-axis at -1. All right, and just make sure that all of those lines have the same slope of -1, and you're good to go. Now we could continue on forever. We could get more and more level curves for different values of c, but this is going to be good enough to get an idea of the surface that we're working with here. All of the level curves for this surface are evenly spaced apart. That's not always going to happen, even when you pick values of c that are evenly spaced apart. It just happens to be the case that that's how it worked out here. And so there doesn't seem to be a whole lot of curvature going on for this surface, which does make sense because this surface is actually a plane. If you were to look at the actual graph of the surface here, it is just a plane in 3D space. And so you can see the 3D render that I have here on the screen. I've included some level curves right there on the surface. In fact, I've included more level curves than what we actually sketched in our contour map, but that's just to help you get a better visual. You don't actually need to graph that many. But if you were to look at this surface from the top down so that you're looking at the XY plane, you can see that you get a very similar contour map to the one that we sketched here. All right, and so that's it for this example. We described the level curves of the function and then found some level curves and graphed them in an XY plane to get a sketch of a contour map for the function. Let's take a look at another example. Once again, we want to describe the level curves of the function and sketch a contour map of the surface. This time around, our function f of xy is equal to x² plus 4y². And so once again, the first thing we want to do here is set this function equal to a constant value c. So let's do that. We'll have c is equal to x² plus 4y². And then what we want to try to do is get this equation in a form that we recognize how to graph. We want to get it in the form of some type of curve that we are familiar with graphing. And in this case, notice that both x and y are being squared. So it's most likely the case that we are working with some type of conic section. And notice that both of the terms are positive. So that means we're either working with a circle or an ellipse. And in this case, it will be an ellipse because the coefficients of x² and y² are not the same. All right, we have 1 for x² and 4 for y². And we could further see that by getting this equation in the form of an ellipse, which you could do by dividing both sides of the equation by c. If you do that here, and I'm going to flip the sides of the equation, I just like to have the variables on the left side. It doesn't really matter, but we're going to have x² divided by c plus 4y² divided by c, and that will be equal to 1, because c divided by itself is 1. And now we can recognize this equation to be in the form of an ellipse. All right, so that's how I would describe the level curves here. They are ellipses. In particular, ellipses that are centered at the origin, because it is just x² and y². You're not adding or subtracting anything to x or y before squaring them. So the ellipses will be centered at the origin. And so let's actually try to find a couple of those ellipses. I always like to start with c equals 0 as my first value of the constant. So I'm going to do that here. And at first that might seem like a problem because you would be dividing by 0 in this equation. But remember, the original equation was this right here. C is equal to x² plus 4y², which does make sense. This equation could be equal to 0 if both x and y themselves are equal to 0. So the equation you get here is x² plus 4y² equals 0, which would ultimately just correspond to a point, right? If you were to graph this, it's really not an ellipse like the rest of our level curves will be. This is just going to be a point because there's only one set of x and y values where this equation is true. This really only translates to a single point, okay? So that is a point, but the rest of our level curves will be ellipses. And so let's take a look at that. Let's move on to c equals 1. Once again, I always like to increase my values of c by 1 each time, or if we're going to go in the negative direction, you would want to decrease by 1. and we'll talk about negative values of c in just a second. For now, let's just focus on some positive ones. When c equals 1, both of these denominators will be 1, so we get x squared plus 4y squared equals 1. Then let's look at c equals 2. Both of those denominators will now be 2, so our equation is x squared divided by 2 plus 4y squared divided by 2 equals 1. But now 4 divided by 2 is 2, so you'll just have 2y squared. I'm going to erase that and rewrite it. We have 2y squared. And then let's look at another value of c. c equals 3. Each of those denominators will now be 3. So we get x squared divided by 3 plus 4y squared divided by 3 equals 1. And then let's take a look at one more. Let's take a look at c equals 4. And for that value, each of these denominators in this equation will be 4. So we get x squared divided by 4 plus 4y squared divided by 4 equals 1. But those 4's would cancel out, so you'll just get y squared. All right, so x squared divided by 4 plus y squared equals 1 is the level curve at c equals 4. All right, so now we have a lot of level curves here, but they were all for positive values of c. What would happen if we looked at some negative values of c? Well, we really can't, right? If you think about our equation here, c equals x squared plus 4y squared, this function will never output a negative value because x and y are being squared, which makes them positive values. Y squared is being multiplied by 4, so it's still positive, and then you're just adding those two values together. So that result will always be positive. This function will never output a negative value, so that constant value we're setting equal to the function can also never be negative. So don't pick any negative values of c here. We're going to be fine just using these positive values, starting with 0, and then 1, 2, 3, 4, and so on. Okay? And so now, let's actually work on graphing these different level curves to sketch a contour map of the surface. Starting with the level curve for c equals 0, we already talked about this. It just represents a point. So this is really easy. I'm just going to plot a point at the origin. That's all it is. When x and y are 0, this equation is true. You'll get 0 is equal to 0. So we plot that point, and that will be the level curve for c equals 0. But then let's move on to c equals 1. We have x squared plus 4y squared equals 1. Now this is where you have to remember how to graph ellipses. Typically the way we go about it is we look at what x squared and y squared are being divided by, and we take the square root of that, and you get plus or minus some constant value that will be the x and y intercepts respectively of that ellipse, assuming it is centered at the origin. All right, but in this case it's a little bit trickier because y squared has a coefficient of 4, but what we can do to fix that is just rewrite it in a different way. 4y squared would be the same as y squared divided by 1/4. So you could rewrite this as y squared divided by 1/4, and that would be the same thing, because dividing by a fraction is the same as multiplying by its reciprocal, and the reciprocal of 1/4 is 4, so 4y squared is the same as y squared divided by 1/4. All right, and so now the denominator of the x squared and y squared terms are 1 and 1/4. So take the square root of those values, and you'll get the x and y intercepts for that ellipse. And so I'm going to write those up here. For c equals 1, our intercepts will be x is equal to plus or minus 1, and y is equal to plus or minus 1/2. All right, x squared is being divided by 1, the square root of 1 is plus or minus 1, and then y squared is being divided by 1/4, the square root of 1/4 is plus or minus 1/2. So those are the intercepts. All right, so if this is x equals 1, x equals 2, y equals 1, y equals 2, x equals -1, x equals -2, y equals -1, and y equals -2. Let's graph the ellipse for c equals 1. Y equals plus or minus 1/2 would be here and here. So the ellipse would look something like this. Okay, so that's the level curve for c equals 1. I'm going to label it like this because we're going to need the space to draw in our other level curves. I'm not going to write c equals 1 in here because we're going to have to write over it. Just remember that this ellipse corresponds to c equals 1. But now let's move on to c equals 2. We have another ellipse. The denominator of x squared is 2 in this case. And then for the y squared term, we have 2y squared. You could rewrite that as being y squared divided by 1/2. So you would be taking the square root of 1/2 in this case to get the x and y intercepts. All right, so for c equals 2, you get that x is equal to plus or minus the square root of 2, and y is equal to plus or minus 1 divided by the square root of 2. All right, now the square root of 2 as a decimal is approximately 1.4, and 1 divided by the square root of 2 as a decimal is approximately 0.7. So our y-intercepts are 0.7 in each direction, and the x-intercepts are 1.4 in each direction. All right, so keeping those intercepts in mind, our ellipse would look something like this. Okay, not a perfect sketch, but that'll do. That is our ellipse for c equals 2. Now let's move on to c equals 3. This time around, x squared is being divided by 3, and then we have 4y squared divided by 3. That would be the same as y squared divided by 3/4. All right, you want to divide it by the reciprocal of that coefficient. So we have y squared divided by 3/4. All right, so for c equals 3, the x-intercepts are plus or minus the square root of 3, and the y-intercepts are plus or minus the square root of 3/4. Or really, that would be the square root of 3 divided by 2, because the square root of 4 is 2. All right, now the square root of 3 as a decimal is approximately 1.7, and the square root of 3 divided by 2 as a decimal is approximately 0.87. All right, or just think of it as 0.9 when you're graphing. So taking those intercepts into account, here's what the ellipse will look like for c equals 3. Once again, not a perfect sketch, but it's good enough. That will be the level curve for c equals 3. And then finally, c equals 4. This is going to be the easiest one to graph. X squared is being divided by 4, and the square root of 4 is plus or minus 2, and y squared is being divided by 1, and the square root of that is plus or minus 1. So the x-intercepts here are x equals plus or minus 2, and the y-intercepts are plus or minus 1. All right, so that ellipse will look like this. That is the level curve for c equals 4. Okay, now we could keep going. You could look at c equals 5, c equals 6, and so on. But I think this is enough for our contour map. 4 or 5 level curves is going to give you a decent idea of the shape of your surface. And so if you were to look at a 3D render of this surface, I'll put one up here on the screen and include some more level curves so you get a fuller picture of the shape of this surface. You can see that our contour map makes sense, especially if you were to take a look at the surface with just the level curves and then view it from the top down so you're just looking at the XY plane. You can see that the resulting contour map matches up nicely with the one we sketched here. It might have some more detail to it, but I would say that our sketch is pretty good. Okay, that's what the contour map would look like for the elliptic paraboloid represented by our given function. Alright, the surface in this case was one of our special types of surfaces, but that won't always be the case when you want to find level curves and sketch a contour map. You can also use this process for non-special surfaces, which is actually when it is the most useful. And you'll see that with a later example in this video. But first, let's take a look at the next example. Hey there, real quick, before we take a look at the next example, if you find my tutorial videos here at JK Math to be helpful, then I'd like to invite you to join my membership site, JK Math Plus, where you get access to many perks, including bonus content and my exclusive community. The bonus content includes dark mode versions of my videos, extra example problems, and more, while the community is a private space online where you can post questions, have discussions, and study together with me and other members. To learn how to join and see a full list of everything you get access to as a member, you can head over to jkmathematics.com/plus. I'll have a link for that in the description of this video. So if you are interested in becoming a member, feel free to check that out. It's a great way to support me and the tutorials I make, as well as a great way for you to learn math better. But for now, let's take a look at the next example. For our next example, we once again want to describe the level curves of the function and sketch a contour map of the surface. And our function this time is f of xy is equal to xy. All right, so we're going to use the same process. The first thing you want to do here is set that function equal to a constant value c. So I'll let c be equal to xy. And then what you want to do is try to manipulate this equation into a form of some type of curve you know how to graph. And so typically when y is to the first power, I like to try to solve for y and see if the resulting equation is something I recognize how to graph. And so if we divide both sides of the equation by x, we'll get y is equal to that constant c divided by x. And that right there is the reciprocal function, right? We have y equal to some constant divided by x. The most common form of the reciprocal function is when you have 1 divided by x. Remember that the graph of that roughly looks something like this, right? This is a rough sketch. I'm going to get rid of that, but that's the general shape that we're working with for this type of equation. Really all that's going to change as this value of c gets bigger in the positive or negative direction is the curve is going to bend or stretch away from the x-axis. All right, so let's look at a couple values of c here. I always like to start with c equals 0, which initially seems weird because it would result in y equals 0, but it would actually give us the line x equals 0 as well. Because if you think back to the original equation here, this expression or this function will output 0 when either x or y are 0, all right, because anything times 0 is 0. So c equals 0 actually gives us two lines of x equals 0 and y equals 0. It's a little bit different than the other level curves we're going to find here. All right, that one's sort of an exception. The rest of them will look like the reciprocal function. Okay, so let's take a look at some of those. Let's look at c equals 1. When c equals 1, you will have y is equal to 1 divided by x. Just replace that c with 1. And then when c equals 2, we'll get y is equal to 2 divided by x. And for c equals 3, we'll get y is equal to 3 divided by x. All right, now remember, when you pick your values of c, try to keep even spacing between them. That's why I go from 0 to 1, from 1 to 2, and from 2 to 3. We're just increasing by 1 each time. But now in this problem, it also makes sense to look at negative values of c. This function can output a negative value if one of these two values, x or y, is negative. So c can be a negative value. That does make sense here. So we want to look at some negative values of c as well. Let's look at c equals -1, c equals -2, and c equals -3. For -1, we'll get y equals -1 divided by x. For -2, y will be equal to -2 divided by x. And for -3, y will be equal to -3 divided by x. All right, so now we have a good set of level curves here to work with that we can graph in this coordinate plane to sketch a contour map of this surface. So let's do that here. Starting with c equals 0, x equals 0 and y equals 0 would make up the level curve. Those would just be the two axes of the coordinate system. Y equals 0 is the x-axis and x equals 0 is the y-axis. So if you want, you can just draw a line over each of those axes like this. That's totally fine. That is the level curve that corresponds to c equals 0. But then moving on to c equals 1, we have y equals 1 divided by x. That's your standard reciprocal function. It has that shape that we talked about earlier, and it will cross through the point 1, 1, right? When x equals 1, you get 1 divided by 1, which means that y equals 1. So if this is x equals 1, y equals 1, x equals -1, and y equals -1, that curve will look something like this. That is at least half of it. You have to remember to draw it over here as well, where it will cross through the point -1, -1, right? The reciprocal function has two curves, one in the first quadrant and one in the third quadrant. That is our curve for c equals 1. But then for c equals 2, we have y equals 2 divided by x. It's going to be a very similar curve to the one that we just drew, except it's going to be a little bit further away from the axes. All right, that constant multiple of 2 is going to stretch the curve a little bit away from the axes. So it would look something like this. That would be the level curve for c equals 2. But don't forget about the other part of it down here. We'll have another curve like this. That's also part of the level curve for c equals 2. And then let's look at c equals 3. We have y equals 3 divided by x, which is just going to be another curve like what we just drew, but even further away from the two axes. So it might look something like this. That would be c equals 3. And I'll draw its other curve like that. All right, so that was all of our positive values of c, or the level curves for all of our positive constants. But now let's look at the negative ones. These are just the negative counterparts of the three curves we already graphed. So really, they are just reflections of these curves. We just want to flip those curves across the x-axis, and we'll have the level curves for c equals -1, -2, and -3. All right, so starting with -1, you'll get a curve like this, and like this. That is for c equals -1. Then for -2, you'll get one like this, and one over here as well. And then for c equals -3, you'll get something like this, and draw one over here as well. And there you have it. That is our sketch of a contour map for this surface. And so if you were to compare it to the actual surface represented by this function, I'll put a 3D render up here on the screen with some level curves included. I've included more than we drew in our sketch, once again, just to give you a better visual of what's going on here and what we're actually drawing. But you can see that the surface sort of looks like a hyperbolic paraboloid. But then if you remove the surface and just look at the level curves, specifically from the top down, so that you're looking at the XY plane, you get a very similar picture to what we sketched for our contour map. Okay, and so that's it for this example. Let's move on to the next one. This time we want to describe the level curves of this function and sketch a contour map of the surface that it represents. And our function is f of xy is equal to x divided by x squared plus y squared. Okay, so once again, what we want to do is set that equation equal to a constant c, and then try to get the equation in a form of some type of equation that we recognize how to graph. And so we'll set c equal to x divided by x squared plus y squared. And then I currently don't know how to graph that, so let's try to make it look a little bit nicer. The only thing I can think to do right now is multiply both sides by this quantity of x squared plus y squared. So that's what I'm going to do first. We'll have c times x squared plus y squared, and that will be equal to x. And then at this point, I'm not really sure what to do next at first, but do notice that we do have an x squared and a y squared term. That's very common in our conic sections, such as with circles or ellipses, and both of them are positive in this case, so it will be one of those two. We're not going to get something like a hyperbola here. And so let's try to get those by themselves. If we divide both sides by c, we'll have x squared plus y squared equals x divided by c. All right, now at this point, I think we're going to have the equation of a circle, because both x squared and y squared have the same coefficient of 1. But we are going to have circles that are not centered at the origin. All right, we have this other x term over here, x divided by c. Typically what we do with an equation that we recognize is going to be a circle is try to get all of those x's into one quantity where you have x plus or minus something squared. In other words, we're going to want to get this term on the other side of the equation and then complete the square for x. All right, so here's our next step. We're going to subtract x divided by c from both sides of the equation. So we'll have x squared minus x divided by c plus y squared equals 0. And now we want to complete the square for our x terms. We have an x squared term, we have an x to the first power term. We just need a constant that's going to allow us to rewrite that as some quantity squared. And so if you remember how to complete the square from algebra, you want to take the coefficient of the x to the first power term, which in this case is negative 1 divided by c. You want to take half of that and square it. All right, so if we take negative 1 divided by c, that's the coefficient of this term. You want to take half of it, so multiply by 1/2. You get negative 1 divided by 2c, and then you square that, you'll get 1 divided by 4c squared. Okay, or really you could just think of that as 1 divided by 2c squared. Okay, that's the constant that we want to add to both sides of this equation. So let's do that here. We're adding 1 divided by 2c squared to both sides, so you want to put it on this side of the equation as well. You're just adding it to 0, so you'll just have that constant, and then you want to add it in here as well. We'll have plus 1 divided by 2c squared. Now because that constant is there, we have now completed the square. You can rewrite these three terms, x squared minus x divided by c plus 1 divided by 2c squared, by writing a quantity of x plus some constant squared. And that constant will be the value you found earlier when taking the coefficient of the middle term and dividing by 2, which in this case was negative 1 divided by 2c. Okay, so here's our new equation. Rewriting it up here, we'll have x minus 1 divided by 2c squared plus y squared, and that's equal to 1 divided by 2c squared, which would just be 1 divided by 2c squared. And I'm going to leave it in that form, that way we can very quickly see what the radius is of each circle. 1 divided by 2c will be the radius, because the x quantity squared plus y squared is equal to the radius squared, so there's no need to square this, just keep the radius in view. Alright, and just to keep my color coding consistent here, I'm going to rewrite that. 1 divided by 2c. Alright, now we have our equation in a form that we recognize how to graph. This right here represents circles centered at the coordinates 1 divided by 2c 0, right? Whatever value is being subtracted from x or y in those squared quantities make up the x and y coordinates of the center. So these are circles centered at 1 divided by 2c comma 0 with a radius of 1 divided by 2c. All right, that's how we would describe the level curves of this function. And so now that we have described the level curves, let's actually find some and then graph them in the xy plane to sketch a contour map. And just like with the other examples, I always like to start with c equals 0, which initially might seem like a problem because plugging 0 into these denominators will result in a denominator of 0, which is undefined. But remember what our original statement was here when we set this function equal to 0? We had c is equal to x divided by x squared plus y squared. C can be equal to 0 if x itself is 0 and y is not equal to 0 at the same time. All right, because you can have 0 divided by some constant that's not 0 and get 0. Okay, so c can be equal to 0, the output of the function can be 0, but only when x is 0. So that would be the equation here, or the level curve. You would just get x equals 0, which is the y-axis. All right, but then let's actually look at some circles here, starting with c equals 1. If you plug 1 in for c in this equation, you'll get the circle equation of x minus 1/2 squared plus y squared equals 1/2 squared. It's a circle centered at 1/2 0 with a radius of 1/2. Let's look at c equals 2. We'll get x minus 1/4 squared plus y squared equals 1/4 squared, right? We're just plugging in 2 for each of those c's, and this is what we get. Then let's look at c equals 3. We'll get x minus 1/6 squared plus y squared equals 1/6 squared. And then that's probably enough for our values of c in the positive direction. We can also look at negative values of c here, right? This function can output negative values. The denominator will always be positive, but if x is negative, we will get negative outputs. All right, so it does make sense to look at negative values here. They'll be pretty similar to these equations right here. It's just that the x-coordinate of the center of the circle will be the opposite. All right, the radius will still be the same because you're going to be squaring that value. Even though it would be negative, you'll get a positive value whose square root would be a positive radius. All right, so I'm going to write these down pretty quickly, but let's look at c equals -1, -2, and -3. We'll have x plus 1/2 squared plus y squared equals 1/4, which would be 1/2 squared. And then for c equals -2, you'll have x plus 1/4 squared plus y squared equals 1/16. That is 1/4 squared. And then for c equals -3, you'll have x plus 1/6 squared plus y squared equals 1 divided by 36. That is 1/6 squared. Okay, so now we have a lot of level curves here that we can graph to create a sketch of a contour map. So let's do that. Starting with c equals 0, we just have the line x equals 0, which is the y-axis. So we'll draw that in here. That right there is for c equals 0. Just remember that technically the origin would not be included with that line, since x and y cannot be equal to 0 at the same time, resulting in an undefined value for the function. You want to keep that in mind as well for the circles that we draw, but to keep our sketch simple, I'm going to draw full circles that cross through the origin. But then let's move to c equals 1. We have a circle with a center of 1/2, 0, and then a radius of 1/2. So let's let this be y equals 1, x equals 1, y equals -1, and x equals -1. Our first circle has a center of 1/2, 0, so it's centered right here, and it has a radius of 1/2, so we'll go up this way and down this way. Our circle will look like this. That is for c equals 1, and you'll get the reflection of that over here for c equals -1, right? The center is at -1/2, 0 with the same radius of 1/2, because the square root of 1/4 is 1/2. So c equals -1 will look like this. That is a circle with a radius of 1/2, and it's centered at -1/2, 0, okay? When you have x plus a constant in that quantity being squared, that means the x-coordinate of the center is the negative version of that, all right? You're always looking for x minus the x-coordinate of the center. But then let's look at c equals 2 and -2, because they are going to be very similar as well. It will be the same circle, but reflected about the y-axis. c equals 2 is a circle with a center of 1/4, 0, with a radius of 1/4. So the center will be right here. That's 1/4, 0. And then there's a radius of 1/4. So we'll go up 1 unit in each direction. So that circle will look like this. That will be c equals 2. And then c equals -2 will be that same circle but reflected about the y-axis. It will have a center of -1/4, 0. So that circle will look like this. That will be c equals -2. And I forgot to label the other one. This is c equals -1. And then finally, let's look at c equals 3 and -3. C equals 3 is a circle with a center of 1/6, 0, and a radius of 1/6, which is not exactly easy to draw at this scale, but it is going to be a circle smaller than c equals 2. All right, 1/6 is about right here or so. It's not a perfect representation of where it would be, but the circle would look something like that. It's a pretty small circle, and so then you could reflect that to the other side of the y-axis as well, and now we have both c equals 3 and c equals -3. Okay, remember this is just a sketch. Those circles don't have to be perfect. As long as they are reasonably close to what they should actually be, you're good to go. All right, and so there's our contour map. We have now sketched all of the level curves that we found for these different values of c. And if you were to compare this to the actual surface represented by this function, I'll have a 3D render here on the screen. You can see it's a very odd surface. It's not one of our special surfaces. And I've included some more level curves on the surface so you can get a better picture of what's going on here. But if you were to remove the surface itself and just look at the level curves, and then view it from the top down, you will get a very similar picture to what we sketched here for our contour map. All right, so our work is correct. And so that's it for this example. Let's take a look at a slightly different example. Okay, so for this example, we want to describe the level surfaces of the function. And our function is a multivariable function of 3 independent variables. We have f of x, y, z is equal to 4x² plus y² plus z². Unlike all of our previous examples, this multivariable function does not represent a surface in 3D, it represents the graph of some 4-dimensional shape. So for a 4-dimensional shape, we don't look at level curves, but rather level surfaces. Surfaces are in 3D, which is 1 dimension less than the actual graph of the function. Just like level curves are in 2D, which help us visualize surfaces in 3D. Okay, so in this case, level surfaces are the result of setting the multivariable function equal to different constant values c. Right? It's the same idea for our level curves, it's just extended to another dimension. And because of that, we're not really interested in sketching a contour map here. That would be pretty difficult and ultimately not worth our time because we don't really know how to visualize a 4-dimensional object anyway. So even if we would graph a set of level surfaces in a 3D coordinate system, it's not exactly helpful for us to do that by hand. Okay, so in these problems, we were just interested in describing the level surfaces, and that's it. We just want to identify the type of surfaces we would get when setting your function equal to different constant values. All right, so in this case, if we set this function equal to a constant c, we'll have c is equal to 4x² plus y² plus z². And this type of equation should look pretty familiar. Each of the variables x, y, and z are being squared. They're all positive, and there is a constant term. And so this right here, we would recognize to be one of our quadric surfaces, specifically an ellipsoid. All right, no matter what constant c you plug in here, this will be the equation of an ellipsoid. Okay, and you could further see that if you were to divide both sides of the equation by c. If you did that, you would get 1 is equal to 4x² divided by c plus y² divided by c plus z² divided by c, and that right there would be the equation of an ellipsoid, specifically an ellipsoid centered at the origin. And as this value of c would get bigger, the larger the radii would be for that ellipsoid. Okay, that is as detailed of a description as you need for this type of problem. Like I said earlier, there's no need to graph any level surfaces. This is all we really need to do. All right, let's take a look at one more example for this video. All right, so for our last example, we have the same instructions. We want to describe the level surfaces of the function. This time our multivariable function of 3 independent variables, f of x, y, z is equal to x² plus y² minus z². And so let's set it equal to a constant c. and see if we can recognize the type of surface that we would get. And in this case, it's actually not going to be the same type of surface for all values of c. All right, in this equation, all three variables are squared, but two of them are positive and one is negative. And so depending on whether c is a positive or negative value, will change the structure of this equation, and it will represent a different type of surface. We know in all cases it's going to be a type of quadric surface, but which quadric surface it is will depend on the signs of those variable terms. All right, so let's start with if c is positive. If c is greater than 0, what will we have? Well, it would be a positive constant, so that won't affect any of these signs. The equation will just have two positive terms, where those variables are squared, and one negative term, where a different variable is squared. That corresponds to a hyperboloid of one sheet. And if you need to review the forms of the equations of the different quadric surfaces, feel free to go back to my lesson on quadric surfaces, but I'm assuming at this point that you are familiar with those different equations. So that takes care of the positive values of c, and notice that I did not include 0 in that, because if c is 0, then we get an entirely different type of surface, right? When c is 0, there is no constant term, but you still have two positive squared variable terms and one negative. That corresponds to an elliptic cone. All right, so for c equal to 0, our equation is in the form of an elliptic cone. And now finally, let's look at negative values of c less than 0. When c is less than 0, that constant is negative, but we want the constant in the equation to be positive, so we would multiply both sides of the equation by -1, which would flip all the signs of those variable terms. So instead of two positive terms and one negative, we'd have two negatives and one positive. And that corresponds to a hyperboloid of two sheets. That is the form the equation will be in. All right, and that right there would be the final answer to this example. You could get more specific with how you describe each of these surfaces. You could say that they are directed along the z-axis, but I think what we have written here is sufficient enough. We have identified the different level surfaces that we would get for this function depending on the value of that constant c that we're setting the function equal to. And so with that, that is it for this example, and this was also the last example for this video. But if you want to get some more practice with multivariable functions, as well as with level curves and contour maps, I have another example available on my membership site. So if that's something that interests you, feel free to look into becoming a member. You can find all the details on my website at jkmathematics.com/plus. If you have any questions, please let me know in the comments. But if you don't have any questions, this is all I had for now. So I will see you next time.